样一个定理，它的证明长约1万到15000页，散在大约500篇论文里，出自大约100个人之手，前前后后写了30年。而最让人惊讶的是，今天这个世界上没有任何一个人完整的懂这整个证明。上一集我们看着连续对称的数学被搬回了有限的世界，排成一条条规整的家族，可这些对称的原子数学把整套方正群本来只要求一件事，保持长度，而有群做的是把这条要求里的一个操作换成它在有限域里的镜像版本，就这么换掉一个操作，一组全新的群就被扭了出来。这就是扭最具体的样子。那5个例外为什么这么特别？根子在一种叫八元数的数系上。我们从最熟悉的实数出发，每往上翻一倍就得交出一条性质。实数能排成一条线，能比大小，翻一倍到负数，就再也没法把所有数排成一条直线了，比大小丢了。再翻一倍到4元数，它有4个方向，还有 ijk， 这一次丢的是交换律 i 乘 j 等于 k， 可 j 乘 i 却等于负 k， 先后一换，差一个正负号。再翻一倍到8元数，8个方向，连结合律都保不住了，先乘前2个，再乘第3个，和先乘后2个，结果又差一个负号。而要是再往上翻到16维，最后一条也垮了，会冒出2个非零的数，相乘竟然得0，除法彻底做不成。所以这种既除得动又有长度的数系，正好在8元数这一级封顶。全世界总共只有4种，那5个例外群恰恰全都长在这条阶梯的最后一级最反常的8元数上。为什么偏偏是5个？根就在这里。而其中最干净的那个例外群，恰好就是8元数自己的对称群。也就是所有能连续搅动这套8元素乘法，却让规则纹丝不动的对称。故事本该到此为止，可当我们追问这16组连同循环群、交错群，真的就是全部吗？会不会有哪颗原子根本不从这套方法里出来？要回答这个问题，得先有人换一个角度看问题。谢瓦莱他们是把这些群算出来的，用矩阵用方程，可一个更根本的问题一直悬着：这些群到底是什么东西的对称？正多面体群转的是一个柏拉图立体。 随着时代发展，还有第二种回答，让机器来验。2012年，一个叫冈蒂埃的人带着15人的团队，用一个叫科克的证明助手，把那整整255页的奇阶定理逐行机器验证了一遍。机器读完了，确认了每一步。而7年之前的2005年，正是同一个冈蒂埃，已经用同一套办法把四色定理也验过了。同一个人用同一把机器复合的钥匙，先后为四色和有限单群分类，各开了一道可核查的门。但事实上，即便到今天，被机器验过的也只有奇阶定理这一块，整个10000页还远没有。这条几何路后来分量极重。2008年，蒂茨和下一章的主角汤普森一同拿了阿贝尔奖数学界的最高荣誉之一，以第3集那位英年早逝的阿贝尔命名。蒂茨给了我们看清这些群的眼睛可清单到底全不全，得有人真的去证，而这用掉了大约100位数学家整整30年。 代发展还有第二种回答，让机器来演。2012年，一个叫冈蒂埃的人带着15人的团队，用一个叫科克的证明助手，把那整整255页的奇阶定理逐行机器验证了一遍。机器读完了，确认了每一步。而7年之前的2005年，正是同一个冈蒂埃已经用同一套办法把四色定理也验过了。而这场胜利从一开始就裹着不安，连他到底哪一年完成的都对不齐。1981年就有人宣布分类做完了，可也有继承1983甚至1980的，而不管按哪个年份，其实都宣布早了，因为有一大类叫拟泊群的群根本没被妥善处理过。
Hey everyone, welcome to... In this video I'm going to discuss the intrinsic definition of the covariant derivative. This is a continuation of videos 17 and 18 where I discussed the flat space and curved space definitions of the covariant derivative, so please watch those first if you haven't already. The links to those videos are in the description. I'm also going to talk
有这样一个定理，它的证明长约10000到15000页，散在大约500篇论文里，出自大约100个人之手，前前后后写了30年。而最让人惊讶的是，今天这个世界上没有任何一个人完整的懂这整个
bit about geodesics in this video, but my main videos on geodesics are videos 15 and 16, so check those out if you want to learn about geodesics. So previously we learned that the covariant derivative on a curved surface is the rate of change of a vector field v in some direction w with the normal component of the rate of change subtracted. So this is the covariant derivative in the direction of the u coordinate. Also write it using this expression, where the Christoffel symbols represent this formula. We also learned that when the covariant derivative is 0, it means we're parallel transporting a vector along a curve, and I showed you some examples of what parallel transport looks like. And one viewer actually sent me this animation which conveys parallel transport on the sphere really nicely. There's a link to this animation in the description. So in this video we're going to move on to our third definition of the covariant derivative, which is the intrinsic definition for curved spaces. So I'm just going to quickly remind you that there's generally two ways of looking at curved spaces. There's the extrinsic approach, where you look at a curved surface living in 3D space, and you often work with x, y, z coordinates and 3D position vectors. Then there's also the intrinsic approach, where you pretend like you're a little bug that lives on the surface and you have no idea that the outside world exists. So instead of working with x, y, z coordinates in 3D, you would only work with the coordinate lines on the surface, labeled here as u and v. And for this video, instead of calling the coordinates So when it comes to intrinsic geometry, a lot of what we've learned about the covariant derivative is still the same. The formula is still the same, and the concept of parallel transport is still the same. The thing that's going to change, however, is our formula for the Christoffel symbols. You'll notice that the formula for symbols has a dot product in it, and this dot product is actually a big problem for intrinsic space. Previously, when we calculated the Christoffel symbols on the sphere, we expanded all the basis vectors and basis vector derivatives out in terms of the xyz basis. And doing this expansion is what let us compute the dot products. But now, with intrinsic space, we basically have to pretend that the xyz variables don't exist. We can only see the coordinate lines directly on the surface, so we can't expand these vectors out in terms of xyz, and so getting the Christoffel symbols is going to be more difficult in intrinsic geometry. Now, before I show you how to compute the Christoffel symbols, I think it's worth asking why we should care about intrinsic geometry in the first place. I mean, if extrinsic geometry gets the job done, why would we bother making our lives more difficult with intrinsic geometry? Well, one of the main applications of the covariant derivative is in general relativity, where space-time is a curved four-dimensional space. And when Einstein came up with general relativity, he did not think of four-dimensional space-time as living in some sort of higher dimensional space. He didn't make up some higher dimensional origin that we could use to point position vectors at our universe. He just thought of space-time as intrinsically curved, with no outside space existing outside our universe at all. So it's important for us to study intrinsically curved spaces, because they'll help us understand four-dimensional curved space-time. And that means we're going to have to abandon the idea of extrinsic XYZ coordinates and the origin and position vectors that extend from the origin. All we really have is a space with curved coordinate lines. So this brings up one of the main differences between extrinsic and intrinsic spaces. In extrinsic geometry, we define basis vectors as the rate of change of a position vector capital R along curved curves. So the basis vectors end up being the tangent vectors along the curve. But now with intrinsic geometry, we don't really have an origin that we can use to extend position vectors from, since the space is curved. So we can no longer think of basis vectors as derivatives of a position vector capital R, like we do in extrinsic geometry, where we work with vector spaces like R2 or R3. Instead, with intrinsic geometry, the basis vectors we're using are the partial derivative operators themselves. So these derivative operators point in a specific direction, just like ordinary vectors point in a specific direction. So these derivative operators would point in the directions of the u1 and u2 coordinates. And these basis vectors live in the vector space called the tangent vector space at some point P. So given a curved space M, there's a different tangent vector space, TPM, at every point P on the curved space. And we use M here to stand for the word manifold, and a manifold is basically just another word for a curved space. Okay, so let's start computing a formula for the covariant derivative for intrinsically curved spaces. So before we said that the covariant derivative of a vector field is just the ordinary derivative with the normal component of the rate of change subtracted. But since we're dealing with intrinsic geometry now, there's no such thing as the normal vector, since using normal vectors would imply that there's some sort of outside space that we can point into. So we're just going to ignore the normal vector part of this formula. So we just expand the vector field into its components and take the derivative using product rule. So we get a component derivative term and a basis vector derivative term. And recall previously that we expanded out this basis vector derivative as a linear combination of the basis vectors and the normal vector. But again, in intrinsic geometry, there's no such thing as the normal vector, so we just ignore this. So we expand the basis vector derivatives entirely in terms of the basis vectors, using the Christoffel symbols as the coefficients. And we could also write this using the Einstein summation like this. So subbing this in and changing this summation index here to k, we end up with this final expression for the covariant derivative. And this is pretty similar to what we saw before, but the problem ends up being with these Christoffel symbols. Before, we derived an expression for the Christoffel symbols by taking the dot product on both sides with a basis vector, then doing a summation with the inverse metric tensor to get this formula. But again, the problem here is that we have a dot product of basis vectors and basis vector derivatives. And since we no longer have the XYZ extrinsic basis, we can't easily compute these dot products. So we need a new strategy for computing the Christoffel symbols. So to get the intrinsic version of the Christoffel symbol formula, we're going to need to recognize a couple facts. First, we need to remember that the metric tensor components are just the dot products of the basis vectors. And since the order of the dot product doesn't matter, the metric tensor components Gij are the same as the components Gji. So the metric tensor components are symmetric in the I and j indexes. And if you prefer writing things using the derivative operator notation for the basis vectors, you'd write things like this. And you might ask, well, how do we compute this dot product if we can't expand the vectors in XYZ space? Well, the metric tensor is so important that we require the dot products of EI and EJ to be defined for us. So we can either just declare a metric tensor that we already know, so like this metric tensor for the sphere, or sometimes the laws of physics can help us get the metric tensor, like we do here with the Einstein field equations in general relativity, which help us solve for the metric tensor components here. Either way, in intrinsic geometry, the metric tensor needs to be given to us somehow. The second thing I want you to notice is that the derivative of the EJ basis vector in the direction of the UI coordinate really just means this second order derivative here. And since the order of differentiation doesn't matter, that means that this is also equal to the derivative of the EI basis vector in the UJ direction. So if we look at these two basis vector derivative expressions expanded using the Christoffel symbols, and you'll notice that the I and j indexes are reversed here. Since this derivative is equal to this derivative, that means that these two Christoffel symbols are the same. So the Christoffel symbols are symmetric in their lower indexes. If we swap the lower indexes, the Christoffel symbol stays the same. So given these two facts and a bit of mathematical ingenuity, we can actually solve for the Christoffel symbols. So we start by taking the derivative of the IJ metric tensor components in the direction of the UK coordinate. And remember, the metric tensor is just the dot product of the basis vectors. Now, to differentiate this, we're going to sort of use a special version of the product rule that lets us do this. So this is sort of like the ordinary product rule where we have a sum of two terms. In the first term, the derivative is applied to the first factor, and in the second term, the derivative is applied to the second factor. The difference here is that this product rule is working for the dot product of vectors instead of working for ordinary multiplication. So the property that lets us do this is called metric compatibility. So this metric compatibility isn't too important right now, but it's going to be very important in the next video when I cover the abstract definition of the covariant derivative. Anyway, we can replace these basis vector derivatives with the Christoffel symbol formula, and the Christoffel symbols are just scalars, so we can take them out in front, and these dot products are just the metric tensor components. Now remember, we're free to switch the indexes of the metric tensor, so I'm going to go ahead and switch the out to differentiate this. Stays the same. Doesn't matter. That means that this is also equal to the derivative of the EI basis vector in the UJ direction. So if we look at these two basis vector derivative expressions expanded using the Christoffel symbols, And you'll notice that the I and j indexes are reversed here. Since this derivative is equal to this derivative, that means that these two Christoffel symbols are the same. So the Christoffel symbols are symmetric in their lower indexes. If we swap the lower indexes, the Christoffel symbol stays the same. So given these two facts and a bit of mathematical ingenuity, we can actually solve for the Christoffel symbols. So we start by taking the derivative of the ij metric tensor components in the direction of the uk coordinate. And remember, the metric tensor is just the dot product of the basis vectors. Now, to differentiate this, we're going to sort of use a special version of the product rule that lets us do this. So this is sort of like the ordinary product rule where we have a sum of two terms. In the first term, the derivative is applied to the first factor, and in the second term, the derivative is applied to the second factor. The difference here is that this product rule is working for the dot product of vectors instead of working for ordinary multiplication. So the property that lets us do this is called metric compatibility. So this metric compatibility isn't too important right now, but it's going to be very important in the next video when I cover the abstract definition of the covariant derivative. Anyway, we can replace these basis vector derivatives with the Christoffel symbol formula, and the Christoffel symbols are just scalars, so we can take them out in front, and these dot products are just the metric tensor components. Now remember, we're free to switch the indexes of the metric tensor, so I'm going to go ahead and switch the L and J indexes of the metric tensor here. Okay, so we have this formula here where the derivative of the ij component of the metric tensor with respect to the k coordinate gives us this, with summations over the L index. Now I'm actually going to write out this same formula twice more, but with different indexes. So here I have the derivative of ki with respect to j, and here I have the derivative of jk with respect to I. And those would give us similar formulas, just with the ijk indexes shuffled around a bit. Now I'm going to color code the terms we have in these three formulas. You'll notice that the blue terms here are actually the same, right? Since we're free to swap the lower indexes of the Christoffel symbols, these two terms highlighted in blue are actually equal. And these red terms are also the same, again, since we can swap the lower indexes of the Christoffel symbols. And again, these green terms are also the same. So if we do this derivative plus this derivative minus this derivative, we'd get this. And looking at this expression, the blue terms cancel out, the green terms cancel out, and the red terms get added together. So we have this, and again, these red terms are the same, so I'm just going to combine them together. And I'm also going to sum on both sides with the inverse metric tensor, and that will cause the metric and inverse metric to cancel out and become a Kronecker delta on the left. Side here. And you'll notice I've also divided by 2 on both sides, so we get a factor of 1/2 over here. And using the Kronecker delta index cancellation rule, I can cancel the L's and write M. And we get get this. So this is our new formula for the Christoffel symbols. And this completes our definition of the covariant derivative that works for any intrinsically curved space, as long as we're given the metric tensor. So let's do a sanity check and make sure this formula works. You'll remember in the last video we computed the Christoffel symbols on the sphere to be these. So let's recompute these symbols using the new formula. So we know the metric tensor for the sphere is this, and this would be the corresponding inverse metric tensor. Now if we took the derivative of these tensor components, the only non-zero term would be taking the derivative of the g22 component with respect to the u1 variable. And that would give us 2 times sine of u1 times cos of u1, which would also be equal to sine of 2 times u1. All the other metric tensor component derivatives would be 0 for all other combinations of I, j, k. So given these two facts, let's compute the Christoffel symbol for I equals 2, j equals 2, k equals 1. So we sub in 2 for I, 2 for j, and 1 for k. Now, this derivative is the special non-zero derivative we have here, partial g22 by partial u1, and all the other derivatives go to 0. And looking at the inverse metric tensor here, in the second column, the only non-zero element is the u1 variable, and that would give us 2 times. In the last video, we computed the Christoffel symbol. This completes our definition of the covariant derivative that we're over here. I have this, and again, these red terms are the same, so I'm just going to combine them together. And I'm also going to sum on both sides with the inverse metric tensor, and that will cause the metric and inverse metric to cancel out and become a Kronecker delta on the left side here. And you'll notice I've also divided by 2 on both sides, so we get a factor of 1/2 over here. And using the Kronecker delta index cancellation rule, I can cancel the L's and write m, and we get this. So this is our new formula for the Christoffel symbols. And this completes our definition of the covariant derivative that works for any intrinsically curved space, as long as we're given the metric tensor. So let's do a sanity check and make sure this formula works. You'll remember in the last video we computed the Christoffel symbols on the sphere to be these. So let's recompute these symbols using the new formula. So we know the metric tensor for the sphere is this, and this would be the corresponding inverse metric tensor. Now if we took the derivative of these tensor components, the only non-zero term would be taking the derivative of the g22 component with respect to the u1 variable. And that would give us 2 times sine of u1 times cos of u1, which would also be equal to sine of 2 times u1. All the other metric tensor component derivatives would be 0 for all other combinations of I, j, k. So given these two facts, let's compute the Christoffel symbol for I equals 2, j equals 2, k equals 1. So we sub in 2 for I, 2 for j, and 1 for k. Now, this derivative is the special non-zero derivative we have here, partial g22 by partial u1, and all the other derivatives go to 0. And looking at the inverse metric tensor here, in the second column, the only non-zero element is the 2 element at the bottom. So this tells us that m equals 2 is the only m that we care about, because the g12 component just goes to 0. So we sub this term in for the g22 term of the inverse metric components. So this is the formula for the Christoffel symbol 2, 2, 1. And we can cancel the 1/2 and the 2, and we can cancel out one of the signs here. So we get that the 2, 2, 1 Christoffel symbol equals cos over sine, or in other words, cotangent of u1, which is exactly what we would expect. And that's also equal to the 2, 1, 2 Christoffel symbol, since we can swap the bottom indexes without changing the answer. Now let's try the I equals 1, j equals 2, k equals 2 case. So subbing in, we get this, and all the derivatives go to 0 except the partial g22 by partial u1 derivative. And now in the first column of the inverse metric, only the g11 element is non-zero. So this tells us that we only care about m equals 1. So we sub this value in for the g11 metric component. And taking this result, we can turn all this into sine of 2 times u1, which gives us the answer that we were expecting. So if you work it out, all the other Christoffel symbols go to 0, and we get the exact same Christoffel symbols as before, except this time we computed them completely intrinsically without using the x, y, z variables. So the intrinsic formula for the Christoffel symbols gave us the same result as the extrinsic formula, and this isn't too surprising, since if we recall that the derivative of the gij metric component is given by this, and also recall that partial ej by partial ui is equal to partial ei by partial uj, when we compute this expression here, we get this. And after color coding the terms that are equal, the blue terms will cancel, the green terms will cancel, and the red terms will add together to give us this. So these three metric derivatives added and subtracted together are equal to this. And so you can see that when converting this into this and canceling the 1/2 and 2, we end up with the extrinsic formula that we're used to. So it's possible to start with the intrinsic formula for the Christoffel symbols and derive the extrinsic formula we saw in the last video. So to summarize, when we compute this expression, that the derivative of the symbols as before, except this time we computed them completely intrinsically without using the x, y, z variables. So the intrinsic formula for the Christoffel symbols gave us the same result as the extrinsic formula, and this isn't too surprising, since if we recall that the derivative of the gij metric component is given by this, and also recall that partial ej by partial ui is equal to partial ei by partial uj, when we compute this expression here, we get this. And after color coding the terms that are equal, the blue terms will cancel, the green terms will cancel, and the red terms will add together to give us this. So these three metric derivatives added and subtracted together are equal to this. And so you can see that when converting this into this and canceling the 1/2 and 2, we end up with the extrinsic formula that we're used to. So it's possible to start with the intrinsic formula for the Christoffel symbols and derive the extrinsic formula we saw in the last video. So to summarize this video, in intrinsic geometry, we can't make any reference to the outside space. So that means that there are no surface normal vectors and no position vectors. We require the basis vectors at a point to be the partial derivative operators of the coordinate variables at that point. And using the facts that the metric tensor is symmetric in its indexes, that the Christoffel symbols are symmetric in their lower indexes, and also using this special metric compatibility property, we can derive the intrinsic formula for the Christoffel symbols. And this works for both intrinsic and extrinsic cases. It's just that the intrinsic case only relies on the metric tensor being defined and doesn't depend on our ability to use the x, y, z variables in the outside space. And since the covariant derivative formulas end up being the same for both intrinsic and extrinsic spaces, the idea of parallel transport works the same for both. So this would be a vector getting parallel transported along the equator of a sphere, and this would be the vector getting parallel transported along a circle of latitude at a higher latitude. Now, I'm also going to throw in one last fact about geodesics. Again, I talk about geodesics a lot in videos 15 and 16, but the covariant derivative gives us a new way to define geodesics that we haven't seen before. So remember, geodesics are the curves we get when we just walk in a forward direction in a curved space. And we can define this idea of walking forward using the covariant derivative. The idea of walking forward on a curved space is captured mathematically by the idea of parallel transporting a vector along itself. So remember, parallel transport means that the covariant derivative of a vector is equal to 0. So when we say that a vector is parallel transported along itself, we mean that the vector that we're taking the covariant derivative of and the direction that we choose are the same. So when the covariant derivative of a vector in the direction of itself is equal to 0, the resulting curve that we get is a geodesic curve. So if our curve is a function of some curve parameter lambda, then the tangent vectors along the curve would be given by the derivative operator d by d lambda. So a geodesic curve is described by the covariant derivative of the d by d lambda vector in the direction of the d by d lambda vector, and the geodesic would set this covariant derivative equal to 0. So to take this covariant derivative, we just take the d by d lambda vector and differentiate it in the direction of the d by d lambda vector. Now we can expand d by d lambda out using multivariable chain rule and write it as a linear combination of these basis vectors. And remember, these are defined as the EJ basis vectors. Now to take the derivative of this with respect to lambda, we need to use product rule. So we get two terms, the first where we take the derivative of this, and the second where we take the derivative of this. Now, here we're just taking the derivative with respect to lambda twice, so we can rewrite it as a second order derivative like this. And to figure out what this second term means, we can again replace this d by d lambda vector as a linear combination of these basis vectors using multivariable chain rule. And remember, this is just like the EI basis vector. So now here we have two derivatives, and now we can turn this into a second order derivative, which differentiates with respect to uj and ui. Okay, so we have this expression here, and I'm just going to rewrite this and this using the vector notation for the basis vectors. It's still the same thing, I'm just writing it out slightly differently. And remember, we can expand these basis vector derivatives out using the Christoffel symbols like this. So subbing this into here, we'd get this. And finally, replacing this summation of j as a summation over k, we can factor out the ek basis vector and get this. And if you've watched my previous videos on geodesics, this formula should look very familiar to you. This set of differential equations are the geodesic equations. So any curve parameterized by lambda that satisfies these equations is considered a geodesic. It's just that now we're defining a geodesic to be a curve resulting from parallel transporting a vector along itself. And speaking in plain English, a geodesic is just a curve that we get from walking straight forward in a curved space. So it's like the straightest possible path in a curved space. Now, if this formula looks like a bunch of nonsense to you, I would encourage you to watch videos 15 and 16 to learn more about geodesics. I go through an example of finding geodesics on the sphere in video 16. So that was the intrinsic definition of the covariant derivative and a little bit of information on geodesics. In the next and final video on the covariant derivative, I will give you the abstract definition of the covariant derivative, which lets us take the covariant derivative of general tensor fields, not just vector fields. In this video, I'll be explaining the abstract definition of the covariant derivative. derivative. If you're just joining this series now, you'll probably want to watch videos 17, 18, and 19 first, so you can understand the easier definitions of the covariant derivative first. The link to those videos are in the description. So the abstract definition of the covariant derivative is the last definition I'm going to cover, and it's going to be the hardest one because it's mostly just pure algebra. Also, in this video, I might use any one of these three symbols to represent basis vectors. This one here is new, but it's the same thing as the other two. It's just a partial derivative in the direction of the kth coordinate. So when it comes to the abstract definition of the covariant derivative, there are basically two main reasons why we'd want to study it. The first reason is that using the abstract definition, we're going to find that there are actually several different covariant derivatives, not just one. So the abstract definition of the covariant derivative is more general than what we were using before. However, there's still going to be one main version of the covariant derivative that we care about, and that is called the Levi-Civita connection, which comes from the fundamental theorem of Riemannian geometry. The second reason for using the abstract definition is that it allows us to extend covariant derivatives to all tensor fields, and that includes scalar fields, vector fields, covector fields, metric tensor fields, as well as all other tensor fields. And to help you understand how we invent the abstract definition of the covariant derivative, I'd like to talk about how we invented the idea of vector spaces, because vector spaces are a somewhat abstract idea as well. So you're probably familiar with R2, which is the set of pairs of real numbers. And the members of the set R2 serve as an inspiration for vector spaces. So let's look at some properties of the elements of R2. So this might be pretty obvious, but we find that there's a reasonable way to add two elements of R2 together, right? We just add the top numbers together and add the bottom numbers together, and we get a new member of R2. So this property shows that given two members of R2, we can define their sum, which is also a member of R2. Similarly, there's also a reasonable way to scale elements in R2. We just multiply the top and bottom numbers by the scalar, and we get a new element. In this video, In this video, I'm going to discuss this. In this video, I'm going to expand on my speaking and formally. In this video, I'll be introducing acceleration. We mean that not only we need to look with respect to so, and again, we know for sure that this part called the second fundamental form answer components gives us the Kronecker delta. So we can sum on both. Okay, so we've cleaned things up a bit, and again, we know for sure that constant speed. So we know that this path is curved because we see non-zero acceleration vectors, but this path is straight because the acceleration is 0. Now let's consider the equivalent of straight paths on curved surfaces. So again, let's take a look at the tangent velocity vectors along this road. So this path is zigzagging back and forth, but it's also traveling uphill. So the tangent velocity vectors will be zigzagging back and forth, but they'll also be pointing upward somewhat to go up the slope of the hill. And the inclination of the velocity vectors will change depending on how steep the hill is at any given point. So this means that the acceleration vectors, not only will they point inward at these C curves, they will also point slightly upward or downward in certain places when the car's vertical velocity is changing. Now let's take a look at this other road. It moves up and down over some hills, so while the velocity vectors will point forward, they'll also have an upward or downward slope to them. Now, the acceleration vectors will sort of point downward for this C curve here, and they'll point upward for this C curve over here, which is somewhat hidden behind this hill. So you'll notice that both of these roads have acceleration vectors, so neither of these roads is perfectly straight. And that's because the ground surface in both of these cases is curved, so it's impossible to travel in a completely straight line because the ground is curved. But there is a difference between these two roads. This road over here is sort of going as straight as possible in the forward direction, whereas this road over here is sort of wandering back and forth instead of going directly from the start to the finish. So in fact, this path is a geodesic curve because it travels in the forward direction as straight as possible along the curved surface. Whereas this path is not a geodesic because it wanders back and forth. And this difference isn't just something we can see with our eyes, there's a very real mathematical difference between these two curves. You'll notice that on the geodesic curve, the acceleration vectors all exist in the same vertical plane that slices vertically through the path. In fact, all of these acceleration vectors are actually normal to the surface. So just to be clear, when looking at a surface, the normal vectors are always pointing directly out of the surface, whereas tangential vectors will lie in the plane tangent to the surface, which is perpendicular to the normal vector. So the acceleration vectors are always pointing directly in or out of the surface, but never from side to side in a direction that's tangent to the surface. Whereas with this curve that wanders around, the acceleration vectors have a normal component that points directly out of the surface, but there's also a tangential component of the acceleration that points from side to side because the curve is wandering around. So this brings us to our definition of a geodesic curve. In curved space, a geodesic path has zero tangential acceleration when we travel along it at constant speed. So when we say zero tangential acceleration, we mean that the acceleration vector is always pointing directly out of the surface in the normal direction. So now that we have a definition for geodesic curves, we need a plan to find geodesic curves on a surface. So to compute geodesic curves, we need to find curves whose acceleration vector is only pointing in the normal direction to the surface. So the acceleration vector will normally have a normal component and a tangential component, and we need to find curves where the tangential acceleration is equal to 0, so that only the normal component exists. And this property will give us curves that give the straightest possible path between 2 points. So before we go looking for geodesic curves on surfaces, I'm going to give you a quick reminder of how surfaces and curves work. So usually we start with the two-dimensional UV plane and put the UV plane through some sort of function which stretches and bends it so that it becomes a 2D surface living in 3D space. So a given point in the UV plane will get mapped to some XYZ point in 3D space. And I usually write the function as r of u and v, where r is a position vector in 3D space. And if we want to draw a curve on this surface, we just draw the curve in the UV plane first as a function of some curve parameter lambda, and then we put it through the function to bring it into 3D space onto the surface. So I'm kind of abusing notation here, but I'm using the position vector capital R to denote the curve as r of lambda, as well as the surface, which is r of u and v. And recall that the partial derivatives of the position vector r are just tangent vectors to the surface. So partial r by partial u gives us tangent vectors along the u curves, partial r by partial v gives us tangent vectors along the v curves, and partial r by partial lambda gives us tangent vectors along the curve parameterized by lambda. Alright, so to go after geodesic curves now, we need to look at the acceleration vector along a curve, which is the second derivative of r with respect to lambda. So if you watched video 12 in this series on the metric tensor, you'll be familiar with the tangent velocity vector along a curve, which we've expanded here out in terms of the u and v variables using the multivariable chain rule. So to get the acceleration vector, we just take the derivative of this velocity vector. So that means taking the derivative of this term and this term. So with this derivative, since we have a product of two terms, we need to use the product rule. So the derivative of this term results in two new terms. In the first one, the derivative is applied to du by d lambda, and in the second term, the derivative is applied to the basis tangent vector partial r by partial u. And similarly, we get two extra terms for the v variable portion. So this term and this term are easy enough to understand, but these two terms have the derivative of the u and v basis vectors with respect to lambda. So that is going to take a little bit of work to figure out. So we know by multivariable chain rule that the lambda derivative operator can be expanded out in a linear combination of the u and v derivative operators like this. So d by d lambda of the u basis vector is really equal to this. So we act on the u basis vector with these partial derivatives with respect to u and v. So we get this expression with these two second order derivatives. And we can do something similar for with these two second order derivatives. So originally we had this expression for the acceleration vector, and on the previous slide we've derived expressions for this derivative and this derivative, which are here and here. So we're just going to sub in these expressions here, and we end up with this big expression here. So you'll notice that with this big expression we have two types of terms. These two terms here only involve the first derivative of the position vector r, so we know that these exist in the tangent plane, since first derivative velocity vectors are always tangent vectors. But these other four terms here involve second order derivatives of the position vector r, so we don't know if these lie tangent to the surface or not. So I'm just going to rearrange this expression a bit. And again, these two vectors are definitely in the tangent plane to the surface, and these four terms at the bottom might be tangent to the surface, or they might be normal to the surface, or they might be a mix of both. So this formula for the acceleration is getting pretty ugly, so I'm going to suggest a way to make it look nicer. What I'm going to do is I'm going to replace the u variable with u1 and replace the v variable with u2. And adding these indexes 1 and 2 will allow us to rewrite this big expression using the Einstein summation convention. So these first two terms can be written as a summation like this. It's a single summation over I, where I goes from 1 to 2. And these four terms here can be written as this term with two summations, 1 over I and 1 over j, each from 1 to 2. And we can write this summation because each of these four terms has two single derivatives with respect to lambda, and then one second order derivative of the position vector r. Okay, so we've cleaned things up a bit, and again, we know for sure that this part is definitely a vector that's in the tangent plane to the surface, but these parts over here might not be tangent to the surface. So to go after the geodesics, we need to figure out if this portion is tangent or normal to the surface, or a mix of both. So with this expression, these vectors here, which are second order derivatives of the position vector r, these are the mysteries. We need to understand these better. So these second order derivatives here are just 3D vectors living in 3D space. And that means we can expand them out as a linear combination of 3D basis vectors. So we could expand these out in terms of the standard XYZ vector basis, but we're actually going to choose a different basis instead. We're actually going to use the two tangent vectors from the u1 and u2 coordinates along the surface, which give us a basis for the 2D tangent plane. And for the third basis vector, we're going to use a vector normal to the surface. So what we're going to do is we're going to build these vectors out of a linear combination of these three basis vectors here. These two tangent vectors in the tangent plane and this normal vector. Now, how much of each of these basis vectors do we need? Or in other words, what are the components of this vector in this basis? Well, we don't actually know the components at all, so we're just going to make up new variables for the components since they're unknown. So we're going to use these variables here. These Lij terms, these are called the second fundamental form. And Lij tells us the normal components of this second order derivative with respect to ui and uj. And these capital gamma symbols, these are called the Christoffel symbols, and these give us the tangential components of the second order derivative vector. So gamma 1ij tells us how much of the u1 basis vector we need, and gamma 2ij tells us how much of the u2 basis vector we need. So here is our 3D vector basis with the surface normal vector and the two tangent vectors. So if this is the second order derivative vector that we want, then gamma 1ij would be this component along the first tangent vector. Gamma 2ij would be this component along the second tangent vector direction. And Lij would be this component along the normal direction. Okay, so we have this formula here for the second order derivative vectors. And I'm going to group these two terms together using Einstein notation with a sum over k to make things even more compact. Now, the next thing we need to do is solve for these gamma terms, the Christoffel symbols. So notice that this normal vector n hat is, by definition, always going to be normal to this tangent plane here. And that means that the dot product of n hat with any of the tangent vectors is always going to be 0, because the normal vector and the tangent vectors are perpendicular by definition. So to solve for the Christoffel symbols, we can take this formula here and take the dot product with a tangent vector on both sides. And so we get this, and this term will go to 0 since n hat is perpendicular to the tangent vector. And so on the right-hand side, we're left with the Christoffel symbols summed with this dot product of tangent vectors. But this dot product of tangent basis vectors is just the metric tensor by definition. So we can rewrite this as the components of the metric tensor. So now we have this. And to isolate the Christoffel symbols, we need to get rid of these metric tensor components. So recall that by definition, the summation of the metric tensor components with the inverse metric tensor components gives us the Kronecker delta. So we can sum on both sides with the inverse metric components, and this becomes the Kronecker delta mk. And by the Kronecker delta cancellation rule, we can cancel these k indexes and just write the m index. And so we get this. This is our formula for the Christoffel symbols. And we're not as concerned with the second fundamental form here, but we can also solve for it in a similar way by dotting both sides with the normal vector. Now this term will go to 0 since the normal vector is perpendicular to the tangent vector, and by definition, the length of the normal vector is 1, so n dot n just goes to 1. So this is the formula for the second fundamental form components right here. And if we want a concrete expression for the normal vector, you can just use this formula here involving cross products, where EI and EJ are just the tangent vectors for the UI and UJ coordinates. And since these two vectors lie in the tangent plane, their cross product will always be a vector that's perpendicular to the tangent plane. And we also divide this vector by its length to ensure it has length 1. Okay, so we're done basically all the painful math in this video, and what we have here is our equation for the acceleration vector along a curve right here, where these second order derivatives are given by this formula here, where the Christoffel symbols and second fundamental form are given by these formulas. So if you're wondering why we did all this extra work when this first formula seemed to be perfectly good, you'll notice that if we plug this formula into the second derivatives up here, we get this equation here. And notice how all these terms in this equation are either given using the tangent vectors or the normal vector. So we can actually group these terms together since they're all just multiples of the tangent vector partial r by partial u with index k. So how does that help us? Well, recall our plan all along was to find geodesic curves, which are curves where the acceleration vector is always normal to the surface. And earlier we talked about how we can break up the acceleration vector into a tangential part and a normal part. Well, that's exactly what we've just done with this formula here. We broke up the acceleration vector into a tangential part and a normal part. And if the geodesics are curves where the acceleration vector is always normal, that means that geodesics will always have a tangential part of the acceleration that is equal to 0. So setting this formula here to 0 is an effective way of detecting whether or not a curve is a geodesic. So setting the expression for the tangential component equal to 0 gives us the geodesic equation. So any curve parameterized by lambda, which satisfies this geodesic equation, is in fact a geodesic curve. And these geodesic curves are the paths that beams of light will follow in curved spacetime. So if this geodesic equation looks like a bunch of random nonsense symbols, please watch the next video in the series where I will walk through an example of using this equation to find geodesics on a curved surface. So just to summarize this video, we said that geodesic curves are the equivalent of straight lines in curved spaces and will give us the shortest distance between 2 points. And our definition of geodesic curves on a surface are curves whose acceleration vector points completely in. In this video, I'm going to expand on my explanation of the differences between the gradient operator del and the d operator, the exterior derivative. The original video on del versus d is in a link in the description, so please watch that one first if you haven't already. So if you watched the last video, you should already know the basic differences between del f and df. Del f, which I also called the gradient of f, is a vector field where the vector arrows point toward the positive values of f. On the other hand, df is a covector field where the covector curves are oriented towards the positive. positive values of f. And the way we convert between the components of del f and df are by using these formulas here, which use the components of the metric tensor and the inverse metric tensor for the conversions. Now, in this video, I'd like to cover two other things. I'd like to do a more formal derivation of this formula for the components of df using the tensor product. And if you aren't familiar with the tensor product, I have links in the description to my videos that explain that. And the second thing I'd like to do is to give some examples of computing del f in different coordinate systems. So first, I'm going to give a deeper explanation of this formula. So to explain this formula, we're going to need to understand the tensor product of two covectors. So given this vector basis here, e1 and e2, we can define the covector basis epsilon1, epsilon2 using this formula here. So these are the basis vectors e1, e2, and these are the basis covectors epsilon1, epsilon2. And to figure out the output of a covector stack acting on some vector v, we just count the number of lines that the vector pierces. So in this example, the output would be 2. So given some vectors and covectors, we know how to figure out the outputs. Now, what the tensor product of two covectors creates is a sort of double covector. It's a function that takes two vector inputs, and to compute the output, we just pass the vectors to the covectors like this, and we just multiply the outputs of each of these two covectors here. So speaking informally, these four tensor products of the epsilon basis covectors are kind of like these four matrices here. So this tensor product of covectors acting on the vectors v and w, if we write this in array notation, we would write it like this, using this matrix for epsilon1 tensored with epsilon2. And churning through the array multiplications, we get the first component of v multiplied by the second component of w. And that is exactly the output of epsilon1 acting on v multiplied by the output of epsilon2 acting on w. So when we want to compute the output of the metric tensor acting on two vectors v and w, the output is equal to this summation formula here. Or equivalently, we could write it out in array notation like this. So this metric tensor array here can be written as a linear combination of these matrices. So in a sense, the metric tensor, which takes two vector inputs, is sort of like a double covector. And we can write out the metric tensor as a linear combination of tensor products of covectors, where each of these tensor products is a bit like one of the matrices I showed earlier. And we can write this linear combination using the Einstein notation like this. So the v and w vectors can be written as a linear combination of basis vectors, which can be written in Einstein notation like this, and the metric tensor, which can be written as a linear combination of covector tensor products can be written in Einstein notation like this. So when we want to compute v.w, which is equal to the metric tensor acting on v and w, we can just expand g, v, and w out into their linear combinations. And then we can pass these vectors to the tensor product of covectors like this. And since the covectors are linear, we can take out these scalar constants and put them in front. And these, by definition, will become Kronecker deltas. And finally, we can use the index cancellation rule for Kronecker deltas to get this final formula here. So this is the formula for the dot product of v and w.
I got one challenge for you. Try WhisperFlow once. One time. And I promise you'll understand why.
be written in Einstein notation like this, and the metric tensor, which can be written as a linear combination of covector tensor products, can be written in Einstein notation like this. So when we want to compute v dot w, which is equal to the metric tensor acting on v and w, we can just expand g, v, and w out into their linear combinations. And then we can pass these vectors to the tensor product of covectors like this, and since the covectors are linear, we can take out these scalar constants and put them in front, and these, by definition, will become Kronecker deltas. And finally, we can use the index cancellation rule for Kronecker deltas to get this final formula here. So this is the formula for the dot product of V. Now if we want to compute the components of the covector V dot something, we can just give the metric tensor one vector input and leave the second vector input slot empty. And so we can expand out the metric tensor and the vector v as linear combinations. And we can pass this vector to the first covector as an input, and by linearity we can take these scalars out in front, and this again becomes a Kronecker delta, and we can cancel out the indexes to get this. So as you can see, the covector v dot something can be expanded out as a linear combination of the basis covectors, which are the epsilons. So that derivation relied on an understanding that the metric tensor is a linear combination of covector tensor products, and also knowing how basis covectors act on basis vectors. Now to get the calculus versions of these formulas, we replace these basis covectors with the basis covector fields dCi and dCj, where C stands for Cartesian and C1 equals x and C2 equals y. And these DC covector fields are defined by this formula here, where dCj, acting on the partial derivative of Ci, gives us the Kronecker delta. And these formulas are actually true for any coordinate system, not just the Cartesian one, but I'm going to be using the Cartesian coordinates just to make things simple. So we can use a similar line of thought when calculating del f dot v, which is the same as the metric tensor acting on del f and v. We just expand everything out as linear combinations, where G is a linear combination of covector tensor products, and the vectors are expanded out as linear combinations of basis vectors, which are these partial derivative operators. And we can get the covectors to act on the vectors like this, and then take the scalars out in front, and then turn these into Kronecker deltas, and then cancel these indexes to get this formula. And we saw this in the to get the components of del f dot something, we just remove the vector input and go through the exact same steps. So expand in linear combinations, give the vector to the covector, pull the scalars out in front, turn this into a Kronecker delta, and then cancel the indexes. And so you can see that del f dot something is really just a linear combination of basis covector fields dCj with these as the components. So I've shown you that this formula is correct. Now I'm going to go through a couple examples of computing del f in two different coordinate systems. So this will involve the C coordinate system and the D coordinate system. And in each one, we'll need to compute the inverse metric tensor components and these partial derivatives. And remember that these basis vectors are just the same things as these partial derivative operators. So the C coordinate system will be our standard Cartesian coordinate system, where C1 is just x and C2 is just y, and the basis vectors are these partial derivatives here. Now our D coordinate system will be given by these transformation equations here, so we basically just double the number of grid lines. So you can see that in the C system, this point would have the coordinates 1, 1. But in the D coordinate system, the same point would have the coordinates 2, 2. So just as this formula says, we basically just multiply the C coordinates by 2 to get the D coordinates of the same point. And the reverse transformation would be the opposite, just multiplying by 1/2. So given these coordinate transformations, we can compute the Jacobian matrix, also called the forward transformation matrix. And if you compute all these derivatives, you'll find that you get this matrix here. Now remember that we can use the Jacobian matrix to convert between the basis vectors in each coordinate system. And since the Jacobian matrix is just the identity matrix multiplied by 1/2, we can write these Jacobian matrix components as the Kronecker delta multiplied by 1/2. And if we cancel these indexes, we get this formula here. And this makes sense. It's telling us that the D basis vectors are half as long as the C basis vectors. So remember this formula because we're going to be using it later. Now let's consider the metric tensor matrix for the C coordinate system. Remember that the metric tensor matrix is just a matrix of the basis vector dot products. And for the Cartesian coordinate system, where the basis vectors are orthonormal so that they have length 1 and are perpendicular to each other, the metric tensor is just the identity matrix. So this is basically by definition for the Cartesian coordinate system, the metric tensor is the identity matrix, or if you like, the components are just the Kronecker delta. Now let's compute the metric tensor components for the D coordinate system. These are just the basis vector dot products for the D system. Now remember, in the D system, the D basis vectors are half the length of the C basis vectors, so we can write them like this. And we can pull both of these factors out in front and multiply them to get 1/4. And these dot products of the C basis vectors are just the metric tensor components in the C system, which, if you recall, this is just the Kronecker delta. So the metric tensor components in the D system are the Kronecker delta
这条几何路后来分量极重。2008年，蒂茨和下一章的主角汤普森一同拿了阿贝尔奖数学界的最高荣誉之一，以第3集那位英年早逝的阿贝尔命名。蒂茨给了我们看清这些群的眼睛，可清单到底全不全，得有人真的去证，而这用掉了大约100位数学家，整整30年。
multiplied by 1/4. So it's basically a matrix with 1/4 along the diagonal. And the values of 1/4 make sense, since you'll notice that this square made by the basis D vectors is 1/4 the size of this square made by the C basis vectors. Now let's take a look at the inverse metric tensor. For the Cartesian system, the metric tensor components are the Kronecker delta. So that means that the inverse metric tensor components are also the Kronecker delta, since the inverse of the identity matrix is also the identity matrix. Now for the D system, if the metric tensor components are the Kronecker delta with a factor of 1/4 here, then the inverse metric tensor components will be the Kronecker delta with a factor of 4. Because the diagonal matrix of 4s is the inverse of a diagonal matrix with 1/4. Okay, so that's basically everything we need to figure out about the coordinate systems themselves. Now let's try looking at a function. So let's say we have this function in the C coordinate system here. Now if we wanted to visualize this, the function would look like this, where red are positive values and blue are negative values, and white represents the value of 0. So in order to get a formula for the function in the D coordinates, we need to do these substitutions for the C1 and C2 variables, and so we get this. So the formulas for f in the two coordinate systems are different. Now remember, to compute del f, we need the partial derivatives of f. So it's not too hard to see that if we compute these partial derivatives, we get these values here. Okay, so we now have everything we need to compute del f. So let's compute it in the C system first. So we know that the inverse metric tensor components are just the Kronecker delta, so we can write this and cancel the j indexes to get this. Now if we expand this summation explicitly in terms of C1 and C2, we'll get this. And we can replace these partial derivatives of f with 1 and 2, as we calculated before. So this shows us that the del f vector field has components 1 and 2. Now let's compute del f in the D system. So the inverse metric tensor components are the Kronecker delta multiplied by 4. And again, we can cancel out these j indexes. And again, we can expand this summation out explicitly in terms of D1 and D2, and we get this. And we can replace these partial derivatives with the values of 1/2 and 1. And if we do these multiplications, we see that del f in the D coordinate system has the components 2 and 4, which we could also write like this. So in the C coordinate system, the components of del f would be 1, 2. So that would be a vector that looks like this. And of course, since del f is a vector field, that vector is repeated everywhere in space. But in the D system, the components are 2 and 4, which seems different, but because the basis vectors in the D system are half as long, we end up getting the exact same vector field as before. So the vector field del f is invariant. The geometric vectors are always the same and don't depend on the coordinate system. But the components of del f might
而费特的身世本身就是一段战争的注脚。他生在维也纳，1939年9月1日，被父母送上一列开往安全地带的儿童撤离专列。那一天正是二战爆发的当天，父母原打算2周后跟来，却再没能成行。他此生再没有见过他们。那趟车是驶出维也纳的最后一班。 就是这个人和汤普森占了群论史上最有影响的定理之一，而让整个数学界倒吸一口凉气的是他证明的长度，整整255页，一条定理255页，如果光这一小步就要这么长，那把所有单群分类清楚，会是一项多么看不到尽头的工程。
Might look different in different coordinate systems because the basis vectors in each coordinate system are different. And so to get the correct components of del F in a given coordinate system, we really do need both the partial derivatives of the function f and the inverse metric tensor components for that coordinate system. If we forget about the inverse metric tensor components, then we're going to end up with the wrong answer. So again, all these extra factors in the formulas for del f in cylindrical and spherical coordinates, these are just components of the inverse metric tensor for that coordinate system. So keep in mind that if a textbook ever tells you that the gradient of a function looks like this, or that the del operator is like a list of partial derivative operators, this is really only true in the Cartesian coordinate system, where the inverse metric tensor components are the identity matrix, and they don't really matter that much. But in general, in most other coordinate systems, this isn't true, and we'll need to use the inverse metric tensor components to get the correct formula for del f. In this video, I'll be In this video, I'll be introducing geodesics and Christoffel together and add the bottom numbers together, and we get a new member of R2. So when it comes to the abstract definition of the covariant derivative, there are basically two main reasons why we'd want to study it. The first reason is that using the abstract definition, we're going to find that there are actually several different covariant derivatives, not just one. So the abstract definition of the covariant derivative is more general than what we were using before. However, there's still going to be one main version of the covariant derivative that we care about, and that is called the Levi-Civita connection, which comes from the fundamental theorem of Riemannian geometry. The second reason for using the abstract definition is that it allows us to extend covariant derivatives to all tensor fields, and that includes scalar fields, vector fields, covector fields, metric tensor fields, as well as all other tensor fields. And to help you understand how we invent the abstract definition of the covariant derivative, I'd like to talk about how we invented the idea of vector spaces, because vector spaces are a somewhat abstract idea as well. So you're probably familiar with our R2, which is the set of pairs of real numbers. And the members of the set R2 serve as an inspiration for vector spaces. So let's look at some properties of the elements of R2. So this might be pretty obvious, but we find that there's a reasonable way to add two elements of R2 together, right? We just add the top numbers together and add the bottom numbers together, and we get a new member of R2. So this property shows that given two members of R2, we can define their sum, which is also a member of R2. Similarly, there's also a reasonable way to scale elements in R2. We just multiply the top and bottom numbers by the scalar, and we get a new element in R2. So given an element v in R2 and a scalar real number, the scaled version of v is also in R2. Another property is that we can add elements of R2 either frontwards or backwards, and we end up with the same result. So the order of addition doesn't matter. We also find there's a special zero element in R2, where if we add a vector with the zero element, we get back the same vector. So that's another property. Also, we find each element has a negative version of itself, where if we add the positive version and the negative version together, we get the zero element. So if we keep going, we can gather together a whole bunch of properties that the members of R2 follow. We get some addition properties, some scalar multiplication properties, and some properties for distributing multiplication over addition. Now, given this, mathematicians basically took all these properties and turned them into a definition, and that's the definition of a vector space. A vector space is a set of vectors and a set of scalars, along with rules for addition and scaling that follow all of these laws. So we started with the properties of R2 and use those to define a vector space, which is a more abstract idea. So a vector space is sort of like a generalized version of R2. But given this new definition of a vector space, we can find other examples of things in mathematics that obey the same vector space laws. For example, the set Rn is a vector space. Also, the set of polynomials in the x variable form a vector space, and the set of partial derivatives of coordinate variables also form a vector space, right? We can add and scale all of these things in a way that makes sense and get linear combinations. So the advantage of inventing the abstract idea of a vector space is so that we can take a lot of things that seem different on the surface, but on a deeper level, they behave in a way that's similar. And we can use the framework of vector spaces to understand all these different ideas in math. Now, inventing the abstract definition of the covariant derivative follows a similar process. We start with the definition of the covariant derivative that we're familiar with and look at some of its properties, and then use those properties to create a new abstract definition. And using that abstract definition, we can define many other types of covariant derivatives as well. So let's take a look at a few properties of this covariant derivative that we're used to so we can invent the abstract definition. And just as a reminder, the intrinsic covariant derivative that we're used to from the previous video just takes the derivative of a vector field in a given direction. And after using product rule and defining the Christoffel symbols, we end up with this expression. So let's say we have the covariant derivative of this vector in a direction given by this linear combination. And to save space, I'm actually going to change the partial derivative notation to this. So remember, these are just partial derivative operators. So we just apply the derivative in this direction and then distribute, and then we can change these partial derivatives back into covariant derivatives, and we get this. So we basically just showed that the covariant derivative is linear for the direction vector input. We can either add and scale the direction vectors before taking the covariant derivative, or we can add and scale the results after taking the covariant derivative. So that gives us this property here. We can also take the covariant derivative of a sum of vectors, and turning this into a partial derivative, we get this. And so we can distribute it to both vectors and then switch back to the covariant derivatives. So this shows that the covariant derivative is additive for the vector field part. We can either add before taking the covariant derivative or add after, and we get the same result. Now, if we take the covariant derivative of a vector field scaled by a scalar, we can change this to a partial derivative, and then use product rule, so we get one term with the derivative of the scalar and one term with the derivative of the vector. And then turning these back into covariant derivatives, we see that the covariant derivative basically obeys a kind of product rule, sometimes called the Leibniz rule. Also, taking the covariant derivative of a scalar function is the same thing as taking the directional derivative. This to a so here. We can also take the covariant derivative of a sum of vectors, and turning this into a partial derivative, we get this. And so we can distribute it to both vectors and then switch back to the covariant derivatives. So this shows that the covariant derivative is additive for the vector field part. We can either add before taking the covariant derivative or add after, and we get the same result. Now, if we take the covariant derivative of a vector field scaled by a scalar, we can change this to a partial derivative and then use product rule, so we get one term with the derivative of the scalar and one term with the derivative of the vector. And then turning these back into covariant derivatives, we see that the covariant derivative basically obeys a kind of product rule, sometimes called the Leibniz rule. Also, taking the covariant derivative of a scalar function is the same thing as taking the directional derivative of that scalar function. So this tells us how to compute the scalar derivative in the product. Rule here. And this is actually why we write the covariant derivative using the same notation as the directional derivative. The covariant derivative is basically like a generalization of the directional derivative for scalar fields that also works for vector fields. So we're going to take these four properties and start using them as a new definition for the abstract covariant derivative. So a covariant derivative is an operator with two input slots. It takes a direction vector and then it takes an input field. And then the output would be the rate of change of that field, which would be a new field. And sometimes this covariant derivative operator is also called a connection. And I'll take a couple minutes to explain where the name connection comes from. So let's say I have a spherical surface, which I'm calling S. Now, from previous videos, you should already be familiar with the idea of parallel transporting a vector along a curve, as you can see here. And parallel transport is given by the condition of the covariant derivative of the vector field being 0. Now, what parallel transport is doing is it's connecting the tangent vector space at the red point P to the tangent vector space at the blue point Q. So in the tangent vector space at point P, which we call TPS, the vector points in this direction. And after parallel transporting it along this curve, in the tangent vector space at point Q, which we call TQS, the vector points in this direction. So this is what I mean when I say parallel transport connects vector spaces. It gives us instructions for turning a vector in the tangent space TPS into a vector in another tangent space, TQS. So parallel transport gives us a way to map vectors from TPS to TQS. And since parallel transport is defined using the covariant derivative, it's really the covariant derivative that's providing the connection between the tangent spaces in this curved space. So that's why a covariant derivative is sometimes called a connection, because we can use it to connect different tangent spaces at different points in the curved space. Now, you might recall from previous videos that we defined the Christoffel symbols like this, where we expand the partial derivative of the basis vectors out as linear combinations. And the abstract version of this, using the covariant derivative, would be this. And when we're talking more abstractly, these Christoffel symbols are also sometimes called connection coefficients. Now, it turns out that given the information we have now, we don't actually have enough information to solve for a unique set of Christoffel symbols. And that's why I said at the beginning of the video that there are many possible covariant derivatives. That's because there are many possible ways to define these connection coefficients. But there is a way that we can get a unique solution for the Christoffel symbols, and that's by introducing two new properties called the torsion-free property and the metric compatibility property. And I should probably mention that although I've defined the torsion-free property like this, a lot of textbooks will use this more advanced definition, where this symbol here is the Lie bracket of vectors. And the Lie bracket basically just tests for the difference between the vectors when we apply them in opposite orders. Now in our case, where the vectors are partial derivative operators, since partial differentiation works the same in both directions, the result of the Lie bracket ends up being 0 anyway. So with a 0 Lie bracket, we can use this simplified version of the torsion-free property. There are more advanced situations where the Lie bracket is non-zero, but I'm not going to cover those in this video. So the torsion-free property says that the covariant derivative of EJ in the EI direction is the same thing as the covariant derivative of EI in the EJ direction. It's sort of inspired by this rule with traditional derivatives where the order of partial differentiation doesn't matter. So given the Christoffel symbol expansion of these two derivatives, since these two covariant derivatives are equal, we're forced to conclude that these two sets of Christoffel symbols are equal. So the torsion-free property means that we're free to swap the lower indexes of the Christoffel symbols without changing their value. The second property is the metric compatibility property, and this is sort of a special version of the product rule that's applied to the dot product. So the result of this derivative of this dot product is a sum, where in the first term, the first factor is differentiated, and in the second term, the second factor is differentiated. So this might seem like a really abstract rule, but what this property is really saying in plain English is that when we parallel transport two vectors, their dot product will stay the same. So remember, the condition for parallel transport of a vector is that the covariant derivative of the vector is 0. So these formulas would mean we're parallel transporting the vectors v and u along a curve. So if we take this metric compatibility property and these parallel transport conditions, this means that this goes to 0 and this goes to 0. So the entire right-hand side here goes to 0. And that means that the covariant derivative of the dot product is 0, or in other words, the dot product stays constant. And remember, since the result of a dot product is just a scalar, the covariant derivative of the scalar is just the partial derivative of that scalar. That was one of the 4 properties of the covariant derivative we stated earlier. So if we were to visualize this, if we start with these two vectors v and u and start parallel transporting them along the curve, the angle between these two vectors would stay constant because the rate of change of their dot product is 0. And of course, since the vector v's squared length is just v dot v, the metric compatibility property also means that the vector will have constant length when it's parallel transported along a curve. Now, one consequence of the metric compatibility property can be obtained if we replace these vectors with the basis vectors ei, ej, and ek. And of course, we can replace these covariant derivatives with the Christoffel symbol expansions. And again, we can replace this covariant derivative with a partial derivative since the dot product is a scalar. Now, bringing the Christoffel symbols out in front, we can convert all these basis vector dot products into metric tensor components, so we get this result. Now, I'd like you to notice what happens when we use the torsion-free property and the metric compatibility property together. Using metric compatibility, we can write out these three equations. And these are all basically the same equation, just with the I, j, and k indexes switched around. And let's say we want to compute this expression right here. It's just these two derivatives added together with this one subtracted. So I'm going to color code these terms here. Notice how the blue terms are the same because the torsion-free property lets us swap the lower indexes of the Christoffel symbols. And by the same reasoning, the red terms are both equal and the green terms are both equal. So since this third derivative is negative, I'm going to write negative signs in front of this third equation. And adding all these together, we see that the blue terms cancel, the green terms cancel, and the red terms add together. So this expression is just equal to twice the red term. And if we sum on both sides with the inverse metric tensor, we get this equation where we've solved for the Christoffel symbols. So using the torsion-free property and the metric compatibility property together, we are able to solve for the Christoffel symbols. And that means we found one particular version of a covariant derivative. And the covariant derivative that uses these Christoffel symbols is called the Levi-Civita connection. And this is basically the result stated by the fundamental theorem of Riemannian geometry. And when we're talking about Riemannian geometry, a Riemannian manifold is basically just a curved space where we have a metric for measuring distances. Anyway, this theorem states that there is a unique connection, or a unique covariant derivative, that is torsion-free and has the metric compatibility property. And again, this unique connection is called the Levi-Civita connection, and it's the connection where the Christoffel symbols, which are sometimes called connection coefficients, are given by this equation. So I've basically spent 3.5 videos describing the Levi-Civita connection, which is the covariant derivative we're all familiar with. But at the beginning of this video, I told you that there are other covariant derivatives as well. So let's take a look at an example of another covariant derivative. So this will be a covariant derivative where all the Christoffel symbols are 0, and I'm going to call this the boring connection. So just to remind you from the previous videos, we derived these Christoffel symbols for the sphere, and these were the Christoffel symbols for the Levi-Civita connection. And when we use this covariant derivative to perform parallel transport of this vector along the curve, we ended up with this vector field, where the vector ends up sort of spinning relative to the basis vectors. And this spinning behavior is because the general solution for the vector components during parallel transport along this curve involved sine and cosine with an angular frequency. And the angular frequency depends on the latitude of the curve. So that's parallel transport with the Levi-Civita connection. Now, if we try the boring connection, where all the Christoffel symbols are 0, we'd get a different covariant derivative, where all these terms go to 0. And the parallel transport equations end up being much simpler, just setting these partial derivatives to 0. So the solutions for the vector field components are just constants. So parallel transporting this vector results in the vector always facing the southward direction. So the Levi-Civita connection and boring connection are both covariant derivatives, since they both satisfy these 4 properties. But when we look at the metric tensor for the sphere, only the Levi-Civita connection satisfies the metric compatibility condition. The boring connection always has the right-hand side of this equation equal to 0, and the derivative of this component is not always equal to 0. so the boring connection is not metric compatible. And both the Levi-Civita connection and boring connection can be used to perform parallel transport, but the results of the parallel transport are different, and they end up connecting the tangent spaces on the sphere in different ways. And we can define all sorts of other connections, but most of the time the Levi-Civita connection is going to be the one that's most important to us. So hopefully you see why there are many possible different covariant derivatives. Now let's move on to extending covariant derivatives to all tensor fields. Let's start by defining covariant derivatives for covector fields. So way back in my Tensors for Beginners video number 4, I introduced the epsilon basis covectors, which are defined by this equation here. So when the covector epsilon j acts on the basis vector ei, we get the Kronecker delta ji. And these epsilon covectors act as a basis, so we can write any covector as a linear combination of these epsilon covectors. And in the tensor calculus video number 6, I talked about how, just as this partial derivative is the calculus equivalent of the basis vector ei, this differential duj is the calculus version of the covector epsilon j. So if we take the covariant derivative of a covector alpha, we can expand alpha as a linear combination of the epsilon basis covectors. And then we can use the covariant derivative version of the product rule, or the Leibniz rule. Now, the covariant derivative of a scalar is just the partial derivative, and we can expand the covariant derivative of the basis covectors using this formula here, where these lambda coefficients play a similar role as the Christoffel symbols, but for covectors instead. And changing these j indexes to k, we get this formula. Now, it turns out we don't need to put any more work in to solve for these lambda coefficients. We actually already know what they are. And to show that, I'm going to examine the covariant derivative of a covector alpha acting on a vector v. Now, it's a known fact that every covector can be written as a vector and a dot product, with the right side of the dot product left empty. So in the case of the alpha covector, we're going to say that the alpha covector is equal to a dot something. And so we can write alpha of v as a dot v instead. And we can again use the metric compatibility property to expand this out using a product rule. And now I'm going to convert these a dot somethings back into alphas. Next, we're going to expand everything. So we can expand the covector alpha with the epsilon basis, and expand the vector v with the e basis. And we can expand this covariant derivative of the covector alpha using the formula we derived on the previous slide. And we can expand the covariant derivative of the vector v using our normal well-known formula. So now I'm going to take the VR components outside, since covectors are linear, and we can scale either the inputs or the outputs, and I'm going to take this term outside the covector as well. So epsilon k of ER is the Kronecker delta KR, so we can cancel out the R indexes and get k here. And epsilon k of V is just the component VK by definition. And alpha of EK is the component alpha k by definition. And expanding all this out, we get this. Now notice that this derivative of a product can be expanded using product rule. And the product rule would give us exactly what we see on the right side of the equation here. So because this and this are equal, we can just cancel them from either side of the equation. And looking at this, I'm just going to relabel some of the indexes here. So I'm going to switch the j and k indexes around, and that gives us this. And we can divide both sides by the alpha and v components to get rid of them. So what we found here is that the lambda coefficients are really just the negative of the Christoffel symbols. So the covariant derivative of a covector field has basically the same formula as the covariant derivative of a vector field, except we just have a negative sign here. Now, in addition to vectors and covectors, we can also define the covariant derivative of a general tensor field if we just declare this property here to be true, where the covariant derivative of a tensor product can be expanded out using another version of the product rule, where we get a sum of tensor products where the first term has the first factor differentiated and the second term has the second factor differentiated. So this would let us take the covariant derivative of the metric tensor, because the metric tensor can be written as a linear combination of covector-covector tensor products. So starting with this, we can use the product rule once to get two terms where we differentiate the components in the first term and differentiate the tensor product in the second term. Now we can use this property to differentiate the tensor product and get another two terms. So you'll notice that we can write the covariant derivative of these covector basis vectors, which we said earlier we could expand out using the lambda coefficients, which are equal to the negative of the Christoffel symbols. So making these substitutions gives us this. So given this formula, we're going to try and write all these tensor products of covectors using the same indexes. So we're going to switch the R and K indexes here, and we're going to switch the S and K indexes here. And now we can factor out this tensor product of basis covectors to get this. So you'll notice that the covariant derivative of the metric tensor has two negative Christoffel symbol terms. So there's a pattern going on here. Vectors are 1-0 tensors because they obey one contravariant transformation rule and 0 covariant transformation rules. So they get one positive Christoffel symbol term. And covectors are 0-1 tensors because they obey 0 contravariant transformation rules and one covariant rule. So they get one negative Christoffel symbol term. And the metric tensor is a 0-2 tensor that obeys two covariant transformation rules. So it gets two negative Christoffel symbol terms. So basically, the covariant derivative of an Mn tensor will give us M positive Christoffel terms and N negative Christoffel terms. Basically, the covariant derivative gives us a derivative term for the components and one extra term for every basis vector or covector that we have. So using this rule, we can determine the covariant derivative of any arbitrary tensor. Also, if we recall the metric compatibility property, we can see that this partial derivative is equal to this. And so all of this actually cancels out to 0. So it turns out that the metric compatibility property means that the covariant derivative of the metric tensor in any direction is always going to be 0. Another way of writing this is as follows, where we just leave out the direction vector of the covariant derivative because the covariant derivative of the metric tensor is 0 in every direction. And if you recall the Christoffel symbols that we derived for the sphere, if we compute the covariant derivative of the metric tensor, we do indeed find that the result is equal to 0. And that's true for all curved spaces as long as the metric compatibility property is true. true. So we've learned a lot in this video, but to summarize everything, the abstract covariant derivative is defined using these four properties here, and we can expand the covariant derivative using the Christoffel symbols. Also remember, a covariant derivative provides a connection between the tangent spaces in a curved space, and it does this by providing a definition of parallel transport, which means that the covariant derivative of a tensor is equal to 0. And we introduced the torsion-free and metric compatibility properties. And remember, metric compatibility, if we're speaking in plain English, it just means that parallel transport keeps the dot product of vectors constant as they are being parallel transported. So given these parallel transport conditions, the rate of change of the dot product is 0. And using the torsion-free and metric compatibility properties, we can derive a unique set of Christoffel symbols, which define a unique covariant derivative called the Levi-Civita connection. And this fact is called the fundamental theorem of Riemannian geometry. And remember, while the Levi-Civita connection is very important, it's not the only covariant derivative. We can easily define another covariant derivative just by picking different Christoffel symbols. And different covariant derivatives will result in different instructions for parallel transport. And in total, we've shown the covariant derivative of a scalar field, a vector field, a covector field, and a metric tensor field. And we can use this property to get the covariant derivative of any general tensor field. Anyway, this finishes my discussion of the covariant derivative. I hope you found these videos helpful. In this video, I'm going to talk about the Lie bracket, flow curves, and torsion. For the torsion part, I'm expecting that you already have a good understanding of the covariant derivative. So if you don't understand
但在大约500篇论文里，出自大约100个人之手，前前后后写了30年。而最让人惊讶的是，今天这个世界上没有任何一个人完整的懂这整个证明。上一集的结尾，我们停在一个半成品面前，有个叫迪克森的人，已经会把连续的里裙搬到有限的世界上，可他是一组一组，几乎一个一个手工搬的。经典那几组能对付，可角落里那5个例外，搬起来则极其别扭，他们没有一个统一的造法。连续对称的周期表已经列全了，但把它整张搬回有限世界的那个方法还没被发现。战争在这条线上留下了2道刻痕。第一次世界大战几乎磨掉了法国整整一代数学家。正是在这片空白里，一群年轻人在1934年聚到一起，用一个共同的笔名写书，把整个现代数学重新打一遍地基。这个笔名叫布尔巴基，他不是一个人，而是一群人的化名，名字还来自一场恶作剧讲座。而他最年轻的创始成员之一，正是这一节的主角谢瓦莱。这条几何路后来分量极重。2008年，蒂茨和下一章的主角汤普森一同拿了阿贝。而费特的身世本身就是一段战争的注脚。他生在维也纳，1939年9月1日，被父母送上一列开往安全地带的儿童撤离专列。那一天正是二战爆发的当天。父母原打算2周后跟来，却再没能成行。他此生再没有见过他们。那趟车是驶出维也纳的最后一班。就是这个人和汤普森占了群论史上最有影响的定理之一。而让整个数学界倒吸一口凉气的是他证明的长度，整整255页。一条定理255页，如果光这一小步就要这么长，那把所有单群分类清楚，会是一项多么看不到尽头的工程。而这件事今天正从世纪工程的例外，慢慢变成数学的日常。当下最活跃的数学家之一陶哲轩把它说得很透。一场传统的数学合作很少超过5-6个作者，因为每个人都得信任并核验其他每一个人。可形式化项目却动辄召集素未谋面的几十号人，恰恰是因为机器能让每一小块被独立验证。这正是分类那100位作者的处境。他还点出形式化对哪一类证明最有价值，恰恰就是那种特别冗长又缺人愿意逐行核验的证明。这句话几乎是照着分类定理写的。
For my videos on that. So the Lie bracket, or commutator, of two vector fields u and v is an operation that computes the difference between applying u to v and applying v to u. The Lie bracket is required for understanding the Riemann curvature tensor, as we can see here, and this tensor is related to the Ricci tensor, which appears in the Einstein field equations in general relativity. Another reason to study the Lie bracket is so that we can get a better understanding of torsion and understand what it means for a connection to be torsion-free. And just a reminder, I'll be using any of these 3 notations to denote basis vector partial derivatives. All of these 3 symbols mean the same thing. So the first thing I'm going to ask is, what does it mean to travel along a vector field? Now, another way to think about traveling along a vector field is to consider flow fields. And for flow fields, the vector arrows tell us about velocity. So if we take a look at this example vector field, 1ex plus xey, an object starting here would immediately travel in the direction of the arrows, and it would follow a path like this. So all the arrows along this path would be tangent to the path, and they would indicate the velocity as we travel along the path. Now, if we want to solve for the equation of a path like this, we would write the path as a position vector capital R as a function of a curve parameter lambda, and all these tangent vectors along the curve would be given by the derivative dr by d lambda. And we could expand this derivative out using multivariable chain rule to get this. And these partial derivatives of the coordinate variables are basically like basis vectors, and these derivatives with respect to lambda would be the components. So looking at these components, we end up with two differential equations that we need to solve. So dx by d lambda equals 1 is easy to solve. We just take the integral with respect to lambda on both sides, and we get x equals lambda plus some constant c. And for dy by d lambda equals x, we can replace x with lambda plus c like we have over here, and again integrate both sides. So we get y of lambda equals 1/2 lambda squared plus c times lambda plus some constant k. So these c and k constants basically determine the starting point of the curve, and we're free to pick them to be whatever we want. But for simplicity, I'm just going to choose the starting point at the origin 0, 0, and that would mean that the c and k constants are both 0. And that would give us the curve parameterized by x of lambda equals lambda, and y of lambda equals 1/2 lambda squared. So this would give us a parabolic path like this. And of course, choosing other values for c and k would give us different starting points and different possible paths. So this concept we've just learned about here is called flow curves, or integral curves. These are curves that are always tangent to vectors in the vector field. And it turns out that flow curves will be related to the physical interpretation of the Lie bracket, which I'm going to discuss now. So the Lie bracket involves this expression here. Now remember that in differential geometry, vector fields are really derivative operators. So in each term here, we're taking the derivative of one vector field in the direction of another vector field. So let's take two vector fields u and v, and we'll find the derivative of one vector field along the other. So let's start by finding the change of u in the direction of v. So that's denoted like this, where v is acting on u like a derivative operator. So we can expand each vector field out into linear combinations of basis vectors using their components. And remember, these basis vectors are really just partial derivative operators, so I'm going to rewrite them like this. And now we'll take this derivative using the product rule. So we differentiate the u components in the first term and differentiate the basis vector in the second. And distributing the v components gives us this. Now we can sub in the x and y components here. Normally we'd get 8 different terms from all these summations over I and j, but most of them go to 0 and we only get 2 non-zero terms. So the x component of u is 1 and the y component of v is x. So we sub those in, and the derivative of 1 is just 0, so this goes to 0. And here we have the derivative of the x basis vector in the y direction. And this actually goes to 0 since the x basis vector is constant everywhere in Cartesian coordinates. So in other coordinate systems, a derivative like this might not go to 0, but
上一集的世界上，经典的极其别扭，他们连了，但把它整张搬回有这条几何路之一，地磁得有人用掉了大约100位数学家整整 而这件事经历者因为每个人却每一小块用特别冗长笔写的。
In Cartesian coordinates, it does go to 0 since basis vectors are constant everywhere. So our final answer is the 0 vector. And next, we'll do the opposite. We'll find the change of v along the direction of u. So we go through the same steps, expand as a linear combination, use product rule, and distribute the u components. And looking at the non-zero terms, we can sub in these components, the x component of u, which is 1, and the y component of v, which is x. And the derivative of x with respect to x goes to 1, and again, the derivative of the y basis vector goes to 0, since in Cartesian coordinates, the y basis vector is constant everywhere. And so our final result is just the y basis vector. Now, let's see if the answers we got make sense. So notice that if we travel so we sub those in the direction of v. So that's denoted like this, where v is acting on u like a derivative operator. So we can expand each vector field out into linear combinations of basis vectors using their components. And remember, these basis vectors are really just partial derivative operators, so I'm going to rewrite them like this. And now we'll take this derivative using the product rule. So we differentiate the u components in the first term and differentiate the basis vector in the second. And distributing the v components gives us this. Now we can sub in the x and y components here. Normally we'd get 8 different terms from all these summations over I and j, but most of them go to 0 and we only get 2 non-zero terms. So the x component of u is 1 and the y component of v is x. So we sub those in, and the derivative of 1 is just 0, so this goes to 0. And here we have the derivative of the x basis vector in the y direction. And this actually goes to 0 since the x basis vector is constant everywhere in Cartesian coordinates. So in other coordinate systems, a derivative like this might not go to 0, but in Cartesian coordinates, it does go to 0 since basis vectors are constant everywhere. So our final answer is the 0 vector. And next, we'll do the opposite. We'll find the change of v along the direction of u. So we go through the same steps, expand as a linear combination, use product rule, and distribute the u components. And looking at the non-zero terms, we can sub in these components, the x component of u, which is 1, and the y component of v, which is x. And the derivative of x with respect to x goes to 1, and again, the derivative of the y basis vector goes to 0, since in Cartesian coordinates, the y basis vector is constant everywhere. And so our final result is just the y basis vector. Now, let's see if the answers we got make sense. So notice that if we travel in the v direction, the u vector isn't changing at all. So the derivative of u in the v direction should be the 0 vector, which is exactly what we got. But if we move in the u direction, the v vector field is changing. It's getting stronger in the y direction. So it makes sense that the derivative of v in the u direction is the ey basis vector. So these two derivatives are not the same, and the fact that these two derivatives are not the same has geometrical significance. So I've overlain the u and v vector fields here, and let's pretend we're sitting at the lower left corner right here. And now what I'm going to do is I'm going to draw the flow curves along these vector fields that would result from taking a small step along v followed by a small step along u. So if we take a small step along v and travel along the flow curve, we'll just move upward. And the v vectors are small here, so that means we have a low velocity and we don't move upward very much. And then taking a step along u, we just move to the right, so we end up right here. Now let's go back to our starting point and do the opposite. So we travel along u to the right, and then we travel along v upward. But notice that the v vectors are stronger here, so we travel at a higher velocity and move farther. So you'll notice that where we ended up by walking along u then v is different than where we ended up by walking along v and then u. Right? These paths don't meet each other at the same point. These four lines don't give us a nice closed rectangle. Instead, we get an open shape that has a gap right here. And so the Lie bracket is defined like this. It just computes the difference between these two derivatives. And the result of the Lie bracket is actually the separation between these 2 points. So when we travel along u then v, but if we move in the u direction, the v vector field is changing. It's getting stronger in the y direction. So it makes sense that the derivative of v in the u direction is the ey basis vector. So these two derivatives are not the same, and the fact that these two derivatives are not the same has geometrical significance. So I've overlain the u and v vector fields here, and let's pretend we're sitting at the lower left corner right here. And now what I'm going to do is I'm going to draw the flow curves along these vector fields that would result from taking a small step along v followed by a small step along u. So if we take a small step along v and travel along the flow curve, we'll just move upward. And the v vectors are small here, so that means we have a low velocity and we don't move upward very much. And then taking a step along u, we just move to the right, so we end up right here. Now let's go back to our starting point and do the
这种规模的协作需要一个总指挥，这个人是哥伦斯坦，同行私下叫他教父，他自己给这项工程起名叫30年战争。而最不可思议的是，作为这场战争名义上的元帅，他还同时管着一整个大学的数学系。1972年，他摆出了一份约16部的路线图，30年换来一句话能说完的清单，每一个有限单群都恰好属于4类之一，没有第5类数阶循环群、交错群，16组理型群，外加26个谁都不属于的散在群。
opposite. So we travel along u to the right, and then we travel along v upward. But notice that the v vectors are stronger here, so we travel at a higher velocity and move farther. So you'll notice that where we ended up by walking along u then v is different than where we ended up by walking along v and then u. Right? These paths don't meet each other at the same point. These 4 lines don't give us a nice closed rectangle. Instead, we get an open shape that has a gap right here. And so the Lie bracket is defined like this. It just computes the difference between these two derivatives. And the result of the Lie bracket is actually the separation between these 2 points. So when we travel along u then v, and travel along v then u, the Lie bracket will give us the separation vector between these 2 paths. And in this case, the separation vector is just the EY vector. Now, we can go through the same process with the U vector field and this new W vector field, which equals YEY. And so if you go through the computations, you'll find that W acting on U and U acting on W are both equal to 0. So they're both equal to each other. And again, if we look at the flow curves, we can go along W, and here the velocity is increasing as we move upward. So we start to move slowly and then move more quickly, and then we can move along U. And this actually brings us to the exact same point as moving along U and then moving along W. So the two final points actually end up being the same, and this rectangle closes properly without any gaps. And that's because the Lie bracket for the U and W vector fields is 0. So the separation vector between this point and this point is the 0 vector. And that means that there's no gap and the rectangle closes properly. So looking Looking at these two examples here, each has a pair of vector fields. In the first example, u of v is not equal to v of u. And if we look at the flows along v then u and u then v, we end up with a gap. The rectangle doesn't close properly. And this gap here is exactly described by the result of the Lie bracket, the y basis vector. But since u of w equals w of u, when we look at the two flows of w then u and u then w, we end up at the same point. The rectangle closes properly without a gap because the Lie bracket is equal to 0. And this is really what the Lie bracket does for us. The Lie bracket takes two vector fields and tells us if the rectangle of flow curves closes properly. If the Lie bracket is non-zero, like here, we end up with a gap. But if the Lie bracket does equal 0, we get a nice closed rectangle without a gap. Now, another way to visualize this is to take vectors from the u and v vector fields like this. Now, if we move along u, the v vector is going to change a little bit, and the change is given by how much it moves away from this parallel line. So the change of v in the u
谢瓦莱他们是把这些群算出来的，用矩阵，用方程。可一个更根本的问题一直悬着：这些群到底是什么东西的对称？正多面体群转的是一个柏拉图立体 ，SO3 转的是一个球，每个群背后似乎都该站着一个它在转动的几何对象。那这16组理型群转的是什么？回答这个问题的人是蒂茨。这种规模的协作需要一个总指挥，这个人是哥伦斯坦，同行私下叫他教父，他自己给这项工程起名叫30年战争。而最不可思议的是，作为这场战争名义上的元帅，他还同时管着一整个大学的数学系。1972年，他摆出了一份约16步的路线图，30年换来一句话能说完的清单，每一个有限单群都恰好属于4类之一，没有第5类数阶循环群、交错群。16组理型群，外加26个谁都不属于的散在群。这场胜利从一开始就裹着不安，连他到底哪一年完成的都对不起。 1981年就有人宣布分类做完了，可也有继承1983甚至1980的，而不管按哪个年份，其实都宣布早了，因为有一大类叫拟铂群的群根本没被妥善处理过。这类群的局部结构瘦得特别，瘦到处理大群的那些通用武器都够不着，可它偏偏又剩下海量的零碎情形，得一个一个手工排除，没有捷径。原始证明里这一块的手稿一直没真正写完，直到阿施巴赫和史密斯两个人接手，埋头啃了好些年，写出2卷1200多页，才在2004年补上这最后的缺口，离最早那声完成已经过去20多年。更让人不安的是，核心人物阿施巴赫后来诚实地承认，原证明里许多众所周知的结果其实散落在文献各处，或者更糟，根本就没在文献里出现过。那它还算一个证明吗？而这件事今天正从世纪工程的例外，慢慢变成数学的日常。当下最活跃的数学家之一陶哲轩把他30年的工作，到头来把整个有限对称的世界扫得干干净净，却在角落里扫出了26颗扫不进任何家族的尘埃，26个散在群。而在这26个里，还蹲着一头最大的、最不讲规矩的。它的大小大约是8乘以10的53次方，写出来是一个54位的数。相比之下，地球上所有的沙粒加起来也不过是个20位数，它难以想象，却真实的存在。它有一个名字叫魔群，正是对称与怪兽这个系列，从第1集起就一直指向的地方。那头活在近20万维里，却又和数论对上了某种暗号的巨兽。
U direction is given by this vector here. Likewise, if we're moving along V and look at the U vector,
What's your name, sweetheart? I forgot.
You can just call me ChatGPT.
ChatGPT.
Yep, that's me.
哪一年完成的，都对不起。1981年就有人宣布分类做完了，可也有继承1983甚至1980的，而不管按哪个年份，其实都宣布早了，因为有一大类叫拟伯群的群根本没被土山处理过。这类群的局部结构瘦得特别，瘦到处理大群的那些通用武器都够不着。手工写完，作业画贺完成，已经过去20多年。更让人不安的是，核心人物阿史过去20多年，1200多页，才在2004年补上这最后的缺口，比最早的生完成